In this lesson, we'll extend our derivative rules by talking about the chain rule. The chain rule is a concept that is relatively easy to teach, but very difficult to master. So take the time to really practice these problems. Here's the motivation behind this. If you have a function inside of a function, then what we have is you might have y as a function of some u, with u being some other function, and you'll see some examples of this. Basically, your u is an inside function, with y being an outside function. If we change the value of t, we change the value of u, and if we change the value of u, we change the value of y. So what if we want to take the derivative of y with respect to the actual variable t? We could think about it as delta y over delta t for right now, and we could break it up into two pieces. Basically multiply and divide by delta u. Delta y over delta u times delta u over delta t would end up being the same thing as delta y over delta t. Now, while it's not quite this simple with the proof that would make this work, it is true that these deltas can be replaced by d's. So the chain rule is actually found like this. If you have a function u within a function y, then dy by dt is just dy by du times du by dt. The way that I often say this is the derivative of the outside times the derivative of the inside. But one thing to add here is that when you take the derivative of the outside, you will leave the inside alone. It's just your u, if you will. One way that's also written here in composite functions is if you have f of g of t. You'll take the derivative of the outside, but leave the inside alone, times the derivative of the inside. This topic is best given by example, so let's first talk about the splitting just a little bit. Let's find a value u that represents the inside function, so that then y is a function of u, but it's also a function of t because u is a function of t. So the first one is the natural log of 5t. Basically what I'm looking for is a split point. What is a good outside and what is a good inside? I'm going to let u equal 5t. That's the inside function. That would give me that y would equal the natural log of u. So when you're dealing with natural logs, a good choice for your inside is the inside of the parentheses. That's one of the types of problems you'll encounter with the chain rule. For the next one, I'm going to let u equal the inside of the exponent, the negative 0.013t. The exponent is a good choice for the inside. That gives me p equals e to the u. E to the u is also a simple function to work with. This is the exponential form. Now for the last one, let's let u equal the inside of the parentheses, the inside of that power, if you will. If we do this, then we have w is equal to 2u cubed. This one applies for powers or roots because, again, roots are just a type of power. Just to review one more time, these are basically the three types of problems you'll encounter for the chain rule. The best way to look at it is, for a log, consider the inside being the inside of the parentheses. For an exponential, consider your inside to be the exponent. And for a power or root, consider the inside to be the inside of that power or root. Now let's see if we can take the derivative for the chain rule here. We're going to start off by doing the same type of split. I'm going to let y equal u to the 7th. Notice I'm focusing on the outside first, but that gives me an inside of 5t cubed plus t. So now what I want to do is take the derivative of the outside times the derivative of the inside. So let's do it by a dy by du, that's the derivative of the outside, which would be 7u to the 6th. The derivative of the inside would be du by dt is 15t squared plus 1. Now let's just go through this. Remember the derivative from the chain rule. It would be the derivative of the outside, which was 7u to the 6th. But I'm not actually going to write 7u to the 6th. I'm going to write 7, and then u was 5t cubed plus t. You want to leave the inside alone. That's raised to the 6th power. So that's your 7u to the 6th. And then you'll simply multiply by the derivative of the inside, the 15t squared plus 1. Just to highlight that, that is 7u to the 6th, and actually a u prime is a way you could think about this. So there's the first one. This is a form for powers. Remember, for powers, a good choice of the inside is the inside of the parentheses, the inside of the power. For the next one, a good choice for your inside is your exponent. So I'm going to consider p is equal to e to the u, with u equal to the exponent, 2016t. And then we'll do the same thing. The derivative of the outside is dp by du, and that's just the derivative of e to the u. Well, the derivative of e to the u is e to the u. Remember from the last lesson, that never changes. And then du by dt. The derivative of 2016t, the t goes away because its derivative is 1, and just leaves you with 2016. Now let's do the same thing. P prime will be the derivative of the outside. The derivative of the outside was e to the u, but again I want to put my u back in, the 2016t, times the derivative of the inside, which is your 2016. And I'll rewrite that a little bit as 2016 e to the 2016t. Which shouldn't surprise you. If I was to solve this using e to the kt, I would get k e to the kt, and that's exactly what I have here. So if you don't like that e to the kt rule, you actually don't have to keep it memorized. You can just use the chain rule. The next one is a log setup. So remember, a good choice for the inside in your log setup is whatever's in the parentheses. I'll just say natural log of u, and u would then be x squared plus 1. So we'll take the derivative of the outside as dy by du, that's 1 over u, and the derivative of the inside would be du by dx, which would be 2x. Same thing. The derivative of the outside, 1 over u, let's write it as 1 over x squared plus 1, times the derivative of the inside was the 2x, and I might write this one as 2x over x squared plus 1. The last one is going back to the e form, but this one would require the chain rule. We'll write this as e to the u, and then u would be the negative x cubed, and let's do the same thing. dy by du, the derivative of e to the u is always e to the u, and the derivative of u with respect to x would be negative 3x squared. So y prime is the derivative of the outside, e to the negative x cubed, remember I put in the u right here, times the derivative of the inside, negative 3x squared. So as a final answer, I'll write this as negative 3x squared, e to the negative x cubed. And by the way, I want to point out something. When you take the derivative of an exponential function, you will never change the exponential function. It just gets multiplied by something every single time. Now this method seems a little bit tedious, so let me start showing you how to take the derivative of a function the fast way, the way that starts doing it in a way that you can learn with enough practice. Take this method as far as you can take it. Keep practicing, keep working at it, and see if you can make some sense of it. The outside function would be something involving the fourth power. So let's just call it that, the fourth power. But then the inside is going to be what's actually inside the parentheses, the x squared plus 9. Now, the chain rule is always the derivative of the outside times the derivative of the inside. So the outside function is this fourth power. What do I do with powers? I bring them to the front, and then I subtract 1 from them. So here's how it works. Take the fourth power and bring it to the front. But now, when you do the derivative of the outside, you will always leave the inside alone. So I'm going to leave my x squared plus 9 as is, and then I'll subtract 1 from my power. I'm not finished yet, but this is the start. Again, I took the fourth power and brought it to the front, and then subtracted 1. And I just left the inside alone. Take the derivative of the outside and leave the inside alone. Then I'm going to do times the derivative of the inside, which often I will just write like this. So you have the derivative of the outside times the derivative of the inside, which I haven't taken yet, let me finish it. 4 times x squared plus 9 cubed times 2x. I could simplify that a little bit. Let's write this as 8x times x squared plus 9 cubed. Next example. If you think about the outside and you look at the function, you should see that there is just a log here. There's a 5 in front, so I'll let it be part of that, but I'm just going to say the ln thing is on the outside. For the inside, I'm going to say what's inside the parentheses, t squared plus 2. So what's really going on is when I take the derivative, I need to think about the derivative of the outside. For natural log of u, you would turn it to 1 over u. So anytime you see the natural log, it's just going to become over whatever is here. So I get 5, because that was the coefficient, over 3t squared plus 2. That's the derivative of the outside, because the natural log becomes 1 over whatever was in there, times the derivative of the inside, which again I'll write in this fashion. So you have the derivative of the outside times the derivative of the inside. And when I do that, I get 5 over 3t squared plus 2, and the derivative of 3t squared plus 2 is 6t, which I can then combine to get 30t over 3t squared plus 2. This problem would be an example of the power form of the chain rule. This problem would be an example of the log form of the chain rule. Keep in mind the power form can also include roots. With that idea in mind, for this one, this is a form of the power, and I could use the 1/2 power, but I have a special rule. Remember I told you that the derivative of square root of x has a rule that's so common you might as well memorize it, to be 1 over 2 square root of x. And I'm going to use that right here. The derivative would be using this rule, which would be 1 over 2 times the square root of, leave the inside alone, 3 minus 2e to the 4t, times the derivative of the inside. Just rewrite the inside and I'll put a prime. And by the way, if you get decently good at derivatives that you want to go ahead and calculate this in the same step, feel free. I have no complaint about that whatsoever. I end up with 1 over 2 square root of 3 minus 2e to the 4t, and then I just need to multiply by the derivative of the inside. The 3 is going to disappear, and then I've got a negative 2 for the coefficient, and e to the 4t is the e to the kt rule, whose derivative is always k e to the kt. I get 4e to the 4t. Now let's simplify this just a little bit. I notice the 2's can cancel, and that leaves me with negative 4e to the 4t over the square root of 3 minus 2e to the 4t. This last one fits the format of the E rule that we've talked about. The E rule is the last form of the chain rule, and for the E rule, it will always be that your outside is just e to the u, or e to a power, and the inside is the whole power. So when I take the derivative, again the outside function is e to something, and the derivative of e to the u is just e to the, leave the inside alone. X plus e to the x is my inside. Then I'll multiply by the derivative of the inside. Now I know this looks a little funny with two e's floating around, but the exponent is just x plus e to the x, and that is your inside, whereas your outside is the e to some power. So then I get e to the x plus e to the x, and the derivative of x plus e to the x is 1, plus derivative of e to the x is e to the x, and I'll just leave this as my answer, even though it's a little bit weird looking.